Okay, well, the goal of these 4 lectures that I'm going to give here is to define and partially construct examples of extended conformal field theories. This material is new, and I'm especially grateful to Stefan for giving me the opportunity to give these lectures and to have them be written up. I mean, this is really quite a treat. Okay, so the idea of extended field theory, so not necessarily extended conformal field theory, but extended field theory, goes back to work of Dan Fried in the 90s, and that was in the context of topological field theory. So it's an extension of Atiyah's definition of topological field theory. So according to that definition, a topological field theory is a gadget. So first of all, you fix a number d, which is the dimension of the theory. And a topological field theory in dimension d is a gadget that to every d-1 dimensional manifold will assign a vector space. And to every cobordism, and the cobordism is now d-dimensional between two. So I have a d-1 dimensional manifold here, a d-1 dimensional manifold there, and I put a d-dimensional manifold in between, whose boundary is the union of these two manifolds. And a topological field theory, what it does is that to any such cobordism, it will assign a linear map between the vector space associated to this manifold and the vector space associated to that manifold. And all that should be done in a compatible way, meaning that if I have a cobordism here and another cobordism there, and I glue them together to form a big cobordism, then the linear map associated to the big thing should be the composite of the linear map associated to this half and the linear map associated to that half. And there's another rule, which is that if I have two cobordisms that I put, well, I don't glue them, but I just put them next to each other. So I have one cobordism here between this manifold and that manifold, and another cobordism there between this manifold and that manifold. Then what I want to see is at the level of vector spaces, I want to see a tensor product of the two things. And there too, and at the level of maps, I also want to see the tensor product of the two maps. So gluing goes to composition of linear maps. Disjoint union goes to tensor product of both vector spaces and linear maps. So that's Atiyah's definition of a topological field theory. And saying that we're looking at extended topological field theories instead of just topological field theories means that we're going to assign things not only to manifolds of dimension d-1 and d, but also to manifolds of lower dimension, all the way down to manifolds of dimension 0, namely points or disjoint union of points. Extended conformal field theories were first proposed by Stefan Stolz and Peter Teichner in the context of their project of constructing elliptic cohomology, and that notion gets also mentioned in a review article by Graham-Segal a bit later. But these authors did not provide any constructions of extended conformal field theories, and also it is unclear whether or not they believed that the standard examples of conformal field theories coming from Kac-Moody algebras, coming from Virasoro algebras, whether or not those standard examples extend to extended field theories, whether or not you can make sense of like putting more stuff so that you don't only see manifolds of dimension 1 and 2, but also manifolds of dimension 0. So the goal of these lectures is to sort of give a positive answer to that, to say, yes, these extend. I won't be able to construct the whole thing because it's a complicated task, but there's an ample amount of evidence that this is something that does happen. Anyways, so I should probably start at the beginning and tell you about Gram-Segal's definition of usual, non-extended conformal field theory. And I should also have a disclaimer that Gram-Segal's definition of conformal field theory is certainly not the only possible definition of CFT, of conformal field theory. And it's also not the most mainstream definition. It just happens to be a definition that has become popular among mathematicians. But it's certainly not, I mean, there exist multiple big textbooks about conformal field theory that some of them list many definitions of conformal field theory and that do not even mention Gram-Segal's definition of conformal field theory. So this is just something to keep in mind. Anyways, but it's the one that I will be working with now. So I will abbreviate conformal field theory to just CFT. So bear with me, I'll explain what all these words mean. So a category, I'm guessing that you all know what that is. There's a bunch of objects and a bunch of morphisms. Symmetric monoidal means that there's an operation that takes two objects and splits a new object, which is a product of these two objects. Standard example is in the category of vector spaces. You can take the tensor product of vector spaces, and that is a monoidal structure on the category of vector spaces. It's not the only one. You could also take the direct sum. That's another monoidal structure. But given a monoidal structure, you can ask whether or not, if I do V tensor W, if it's the same as W tensor V. Well, those are not going to be the same as objects, but there's going to be often a chosen isomorphism between V tensor W and W tensor V. And if that isomorphism satisfies the extra property that if you apply it once and apply it another time, the corresponding map from B tensor W to itself is the identity, then you say that the monoidal structure is symmetric. Okay, so what are the monoidal categories that enter in this definition? The first one has as objects one-dimensional, compact, oriented, C infinity manifolds. So what are these things? These are just circles and disjoint unions of circles. And they're equipped with a smooth structure. And the morphisms, there are cobordisms. Equipped with a complex structure in the interior. And let me underline interior to emphasize that this is important. Okay, let me make a few standard pictures that go there. So here's an example of an object. It's a one manifold. I guess it's oriented, so let me put some little arrows. It doesn't look smooth on this picture, but it actually is smooth. And a morphism, well, suppose I have one of those here and another one there. Then a morphism between those two guys is a piece of Riemann surface that has those as boundary. So this is a smooth manifold with boundary equipped with a complex structure on the open interior. So the smooth structure goes all the way to the boundary, and the complex structure is only in the interior. Very good. What is the monoidal structure? It's the operation of disjoint union. So maybe I should also put it here. Disjoint union is the monoidal structure. And that goes to a category whose objects are Hilbert spaces, morphisms are continuous linear maps between Hilbert spaces, and the tensor product operation is the tensor product of Hilbert spaces. So you take, does everyone know what a Hilbert space is? So if I take the algebraic tensor product of two Hilbert spaces, that's not yet a Hilbert space, but there's a canonical way of putting a norm on that so that the completion becomes a Hilbert space. And that's what I mean by this operation. OK, that's it. So that's a conformal field theory a la Segal. Yes?
Source category, is it the composed bordism?
That's right. So if I have one of these and another one, then you need to
you have to extend a complex structure from the whole area.
That's right. Exactly. So the reason why I emphasized this word here is that I'm going to address that point because it's a subtle point, but it's certainly non-trivial.
Along the same lines, like how do you think of the identities in this bordism category?
The identity is well, there's a few different ways of answering that question. One way is to say that there are no identities, and if there's no identities in that category, that doesn't cause any problems in defining what it means to be a functor. It's just that I have fewer things that I need to assign values to, so that's easy. Or you can sort of add identities by hand and say that I have some extra things that are like, you think of them as being infinitesimally thin, that are the identities. The question of identities is a question of definition, and there's no difficulty there. It's just a matter of making a choice. Yes?
How can you talk about like when two things are equivalent without identities?
I'm not talking about when two things are equivalent in this context. I'm just talking about the notion of a functor. You cannot talk about when two things are equivalent without identities, but it doesn't cause any problems in the definition of what a functor is.
In the monoidal structure, you need to sort of say when are two things isomorphic. So for that, it's sort of good to have identities around. So otherwise, the notion of isomorphism is a little funny.
I agree that it's useful to have identities around, but for the purpose of just writing down a definition, you can get away without having identities. But I like having identities around. Anyways, what's the thing which does require work is the operation of gluing of cobordisms. So suppose that I have a cobordism. And a cobordism, you can think of it as being, so here's one way of saying what a cobordism is. A cobordism is a manifold with boundary and equipped with two inclusions of these things. So a bordism between this and that is the data of this purple manifold along with the two maps. So suppose I have such a cobordism, and then I have another one. Then one thing that one can certainly do is glue them together to form a topological space. So here's the topological space that you obtain. Let's see, in this particular example, there's going to be a sort of big hole here and then a small hole there. So this is what you get, and that, well, has inclusions of those two guys, and it also has a submanifold let me call it C, which lives in the middle of that topological manifold. So a priori, that manifold is only equipped with a complex structure away from C. And even more, a priori, it's only equipped with a smooth structure away from C. If I have two smooth manifolds and I glue the boundaries along diffeomorphism, there is no canonical way of extending the smooth structure across. I mean, to find, there's multiple ways, but there's no canonical way of doing so. But there's a theorem. So it, I know it of some unpublished notes by Graham-Segal, but it also appears in the literature in a paper by Radnell and Schippers. So let me put that as a reference. That says that there exists a unique complex structure. Actually, there exists a unique smooth structure and a unique complex structure such that on that topological manifold, which is compatible with the ones given here and there. And these guys actually prove this theorem in a somewhat greater generality than what I need here. They allow these maps here to be less than C infinity. They allow them to be, anyways, I'm just going to use C infinity maps there. But already for C infinity things, it's non-trivial. So the theorem says that there exists a unique complex structure on this extending the given ones. On the two halves. Moreover, this theorem says a little bit more. It says that the curve C that you get here is embedded in a C infinity way inside that manifold, which is something that you want. Careful, the embedding is not analytic. It makes sense to ask, is the embedding analytic? And the answer is, it's not. So that's already a sign that somehow it's a bit tricky. Anyways, a closely related result, which is actually needed in the proof of that theorem. I should say, this operation has a name. That operation goes by the name conformal welding. And it has been studied by a bunch of people, but often they just do it by sort of in a less geometric sense, and then we just like glue two circles together or things like that. And that's what I want to talk about right now. So there's a lemma which comes as a sort of intermediary result before you can prove this, that says that so I know of a survey article by Bell that contains it, and I'm not sure what the original reference is. The lemma says the following. So suppose I have a disk with C infinity boundary, so a subset of the complex plane with C infinity boundary. So this is in C and has C infinity boundary. Then there's the Riemann mapping theorem that says that there exists always a map which is biholomorphic on the interior, so sends the interior of this to the interior of the standard. So this is the standard disk in C, and there's a map F. And it's not quite unique, but you understand very well to what extent this is unique. It's unique up to transformation of the disk, and that's there's 3 degrees of freedom that you can sort of pick. If you say, I want this point to go there, and I want this tangent vector to go there, then it's unique. So the statement of this lemma is that this map that you obtain is C infinity all the way to the boundary. So the Riemann mapping theorem produces a thing which is holomorphic on the interior, and holomorphic certainly implies C infinity. But if the boundary is C infinity, then it happens that it's C infinity all the way to the boundary. Using that lemma, one can reduce this general question to a more specific one. And the more specific question is the following. So I start with 2 copies of the standard disk. So here I have 2 copies of the standard disk, and I have a C infinity diffeo between the boundaries. So from the boundary of the standard disk to the boundary of the standard disk. And then, well, what do you want to do given that? You want to glue them together. Let's see. So then we glue it. So you do the conformal welding operation, and what you get is a Riemann surface, which eventually is going to be shown to be isomorphic to the standard Riemann sphere, CP1, along with a C infinity curve that lives in it. I mean, these are all results that sort of come before this. You sort of use that. The question of gluing is actually a local question. So you may as well replace this manifold by just a small neighborhood of it. And a small neighborhood looks just like a small neighborhood of an arbitrary domain in the complex plane with C infinity boundary. And then you use this thing to say that it actually looks like an arbitrary piece of the standard circle. And then I have 2 pieces of the standard circle that I have to glue to each other. But I may as well assume that I'm gluing the whole circle to the whole circle. And then this is the thing that eventually you need to work hard to show that that is the case. Anyways, I'm not going to show you the proofs of all these things because that would take me too far away in that direction, and I can't do that right now. So let's move on to extended field theories. So the idea of extended field theories is to replace this category and that category by appropriate two categories. So let me first tell you roughly what you expect to encounter, and then I'll spend some time to actually defining these two categories more precisely. So I was planning, well, let's see. So first of all, let me stick to the same colors that I've used there. So if I have a one manifold, then that gets a Hilbert space assigned to it. So I mean, an extended conformal field theory is one of these plus more data. So we're going to find all that. And then if I have a cobordism as there, then we get a linear map. There's a special case which is worthwhile mentioning, which is if the cobordism is actually a closed manifold, then we get a linear map between C and C, between the complex numbers and the complex numbers, and a linear map between C and C, that's just a number. So this is a special case of that. Now we want to also assign things to lower dimensional manifolds, so let me bring them into the picture. So here's a point, or maybe a collection of points. Well, assigned to a collection of points, we have a von Neumann algebra. And I'll come back to explaining what those are. But let me just finish this little list. So now suppose I have a bordism between one collection of points and another collection of points. Well, what one gets assigned to that is an elaboration of this that involves also the algebras. So I have an algebra associated to this zero manifold and an associated to that manifold. So what could you imagine? Well, we get a bimodule, meaning a Hilbert space equipped with two commuting actions of these two algebras. So finally, we can have the most complicated of all these pictures so far, which is, so I have a pair of zero manifolds, and I have one cobordism between them and another cobordism between the same zero manifolds, and then I have a two manifold, which is a cobordism between those cobordisms. And well, associated to that, we have a linear map of bimodules, meaning a map that's compatible with the actions that commutes with the two algebra actions. So this is the rough picture to have in mind. So the objects on the left, yes?
Is this related to the guess that one would have made by saying something like, oh, for points I'm going to assign some categorified version of the Hilbert space, and then for two morphisms some functor, and then for And then for two morphisms, a natural transformation, how would that idea be related to this one?
Okay, so why is a von Neumann algebra the same thing as a categorified version of a Hilbert space? So it's what you can do is replace. I mean, this is not specific to von Neumann algebras, but if I have an algebra, I can think of an algebra as containing roughly the same information as the category of representations of that algebra. So I could say that I say a point goes to a category, meaning the category of representations of that algebra. And there is a way of rephrasing everything so that you don't really lose any. I mean, that it's essentially equivalent to have one or the other. So it's just a matter of choice. I prefer to have algebras, but I could as well have categories there.
I have a question.
Yes.
So these are like objects on the list?
In orange, we have objects. So the points are objects. In green, we have one morphisms. And in purple, we have two morphisms.
In your complicated picture, is the two manifolds both have a smooth structure at those points in the book?
So this is what this slide is for, is to actually make precise the geometry which is here on the left. So maybe now is a good moment to have a little bit less light onto this part of the board. Is that possible to arrange? Let's see. It's on the wall. Oh, I see. West screen. Oh, the little switches. Sorry. Yeah. Anyways. So this picture is very nice, but one needs to say things. It's just like here. I mean, if you just look at it at first, you're like, oh, this is very nice and natural. You just glue things. And then suddenly you try to make sense of what it means to glue, and you realize that there's difficult issues that need to be addressed. The same thing happens with that part on the geometry side. So let me be more specific as to what the objects. So objects are the zero morphisms. It's the first row of this diagram. The morphisms is the second row, and the two morphisms is the third row. Okay, object. Zero manifolds. Oh, I should say everything is equipped with an orientation. I haven't said it here. So there's the positively oriented point and negatively oriented point, and those are different. Zero manifolds, there's no particular structure to put on them apart from the orientation. The local model is just a point, and anything looks locally like a point. The one manifolds. So these are smooth one manifolds. So if M0 is a collection of points, let's see, maybe I should, is there a way of me, I can't point. Maybe I can do this. Here, M0 there. If M0 is a collection of points and M1 is a collection of points, the W that's here in the middle is a one manifold. And this one manifold is equivalent to the smooth structure. But in order to be able to glue one manifolds to each other and to have a smooth structure on the glued thing, then there's no way out. You really need to have a little parametrization of the neighborhood of the endpoints. And that's what I have here. These are called collars. Collar is a little parametrization. The local model is just the interval. Okay, here's the meat of the story. So what's a two-dimensional cobordism? So first, let's look at what I take for local model. So it's exactly this picture that's here below. So this picture sits inside the complex plane, and it is the area between the graphs of two functions. And those functions are required to agree on a little neighborhood here and there. So this is a bad picture. This is not a cusp. This is really, it ends with a piece which is purely one-dimensional at the end. And the functions are smooth, and that's all. So just like in that story, the conformal structure only exists in the interior of of this piece. You also need to have a compatibility between the colors of the top and bottom part. So I said that the one manifold on the top and the one manifold on the bottom really agree here at the beginning, and I also want the parameterization that they come with to agree. That's what these two commutative diagrams say. So this is everything. So let me maybe write down some examples of those, so that you see what can happen. Okay, so okay. Unexpected. Okay, so this we don't need anymore. So these are some examples of this story. So let me be consistent with colors. So first some zero-dimensional examples. Well, so as I said, manifolds are oriented. So I have the plus point and I have the minus point, and then I have disjoint unions of those. That's a complete list of zero-dimensional examples. Here are some examples of so let me use a different color convention. So I'm going to need to talk about what is ingoing and what is outgoing. So in this picture I have the manifold M0 and M1. And one convention that you can use to denote that is to say that everything that's ingoing is written on the left and everything that's outgoing is written on the right. But that's going to be not very convenient for me. So everything that's ingoing is going to be written in, can you see the difference between these two colors? No. Okay, very good. How about between blue and red?
Yes.
Excellent. So in general, blue is going to be ingoing and red is going to be outgoing, and then this one is going to be the color of the thing that I'm drawing. So for example, this is a one morphism between the plus point and the plus point. Here's a picture which is this is a one morphism between the disjoint union of the plus point and the minus point, and the outgoing manifold is the empty manifold.
So you should have this red.
Sorry?
You should have this red on, right?
No.
You said it's out.
This is a morphism between the blue manifold and the red manifold. So the blue manifold consists of 2 points. And this is a morphism from, so this is a morphism from 2 points to 0 points. And so I said I'm not going to use the convention of putting everything that's ingoing on the left and everything that's outgoing on the right. So this is the convention that I use.
So is that first one morphism that you drew an isomorphism?
No. It would be if these two things were sort of on top of each other. Okay, so let's draw some two-dimensional pictures. So I can have the plus point and the plus point here, and then I have the ingoing manifold, which is like this, the outgoing manifold, which is like that, and in between we have a piece of Riemann surface. You can draw the same picture with some other colors, and then it has another meaning. For example, I can have let's see. Here, let me put a little bit of topology in there. And well, that's another example. So the blue and red one manifolds are cobordisms between 2 points and no points. And then there is a piece of Riemann surface that connects those. Yes?
What is the significance of the plus and minus that you put on the
it is an orientation. So there's two possible orientations of a connected zero-dimensional manifold. And I denote them by putting plus or minus.
But there's no compatibility between the orientation and the...
There is a compatibility between the orientation of, yeah, so it's not valid to put a plus here because the orientation on the incoming boundary needs to be the one induced by the orientation there. It's sort of, there's one rule that you need to follow for the blue boundary and the opposite rule that you need to follow for the red boundary. So there are some constraints. If I know the orientation here and the color there, I can deduce if it's plus or minus.
So the surfaces also have an orientation?
Yeah, the surfaces also have an orientation. I'm just not denoting it in that particular picture. So finally, let me draw one final example, which is so that's okay. Let's see. And as with every picture, really these points end up with a piece of one-dimensional thing that sticks out, but it's sort of not drawn there. So this is the picture that I would have difficulty drawing if I had to stick to the convention that everything blue goes left and everything red goes to the right, and then same thing for the one morphism, everything blue is above and everything red is below. It's sort of difficult to draw it. So these are examples. And locally, so around every single point, I should see something which is locally given by that model. Does that make sense? Are you guys following? Okay, so that is all I want to say about the source 2 category.
You always have to have an incoming edge and an outgoing edge when you meet up that.
Yeah, yeah. So this is what happens in this local model. And the local model, this being a local model, means that anything that you see here, if I sort of zoom in into a neighborhood of something, I should be able to zoom in into a corresponding neighborhood there and see the same thing. So you never see in this picture two like blue things forming this sort of cusp behavior, and therefore that's not allowed.
I'm a little confused about the cusp behavior. Is this category you're describing equivalent to what you get if you started with Riemann surfaces and shows mark points and then shows curves between them and cut along them? I'm sort of like, can you glue these pieces together to get an ordinary Riemann surface? The cusps are sort of giving me trouble seeing how that would be done.
I mean, Are you asking me how does one glue these things? Or are you asking me can one build any Riemann surface by gluing together those kinds of pieces?
Whichever you care to answer.
They're both interesting, but they're different questions.
Sure, I'd love to answer both.
So it is possible to glue things together, and I'm going to address that. Oh yeah, I guess I should say that. And then to form an arbitrary Riemann surface, it's not enough to have just those. You need also those.
But the cusps don't give any difficulty even if you thought hard enough about it.
Well, they give as much difficulty as that story and more.
Okay.
So, sorry, Jacob, you have a question?
So, for any f and g of a local model described there, how many different f's and g's do you need?
You need all of them. You need many. You need a large number of local models, depending on like how sharp this cusp is. It's a different local model. Yeah. So let me maybe say a few words about how to glue things together. So because this is a local model, it's enough to know how to glue local models together. Gluing is a local operation. So really the question is, I have two of those guys, and I have a diffeomorphism, a C-infinity diffeomorphism between the bottom part of this guy and the top part of that guy, and I want to make sure that if I glue these things together to form this sort of picture, that, well, it looks like it's again like one of these local models, but it's not explicitly given as one of those local models, and therefore work needs to be done. Using that work, we can make sure that there's a complex structure on the interior. So that's fine. So at least it is something that has this structure. What isn't clear is that it is isomorphic to one of those local models. And the way to do it is as follows. So you take this, and let's embed it into a disk in the following way. So here I put it inside a disk. This is a disk. And I do the same thing here. I embed that one into a disk in that way. And then I extend the C-infinity diffeomorphism to a C-infinity diffeomorphism of the whole disk. So now I'm in exactly that situation. I have two disks and a C-infinity diffeomorphism between their boundaries. So I can use that construction, and I know that I get a picture which is drawn on the Riemann sphere. So if you glue these two disks, what you see is a Riemann sphere with in it the following picture drawn. You see this sort of drawn in this sphere after gluing, because there's like this little piece there and that little piece there, and that's what you see there. Using that lemma, we know that the image of this top pink curve is embedded in a C-infinity way inside that Riemann surface. And using the same lemma, we know that the bottom curve is embedded in a C-infinity way. So I have a C-infinity thing here, and a C-infinity there, and a C-infinity there, and eventually you see that it is of the form given by the local model. But somehow this work is needed in order to make precise how to glue things. Okay, I would like to spend a little bit of time that is left to say what the objects that appear on the right side of that diagram are. So numbers, linear maps, maps of bimodules, Hilbert spaces. Hilbert spaces equal to actions. I'm going to assume that you know what they are, but I'm not going to assume that you know what a von Neumann algebra is. So So it's an algebra over the complex numbers equipped with some additional structure. There's a topology on it. It's typically infinite dimensional. There's a topology on it. And there's a star operation. An operation that satisfies A, B star equals B star, A star. And that's antilinear. So it's a topological star algebra over C that can be embedded in B of H. H is some random Hilbert space, and B of H is the algebra of all bounded operators on H. The embedding into B of H is not part of the data. It's just required to be possible to embed it in B of H. I need to say, so it's supposed to be, so as a closed subalgebra. And also closed under the star operation. So I should say a little bit what the topology, the relevant topology on B of H is, with respect to which we require that this algebra be closed. And so that topology is called the ultra-weak topology. And one way of defining it, I'm running a bit out of time, so I'll just give you the short way of defining it, is to say that there is a pairing between bounded operators and trace class operators given by sending A, B to the trace of the product, A times B. And whenever you have a pairing between two vector spaces, there is an induced topology on, well, on both of them, I guess, but I care about the induced topology on this. So it's a topology induced by the pairing.
The ultra weak, is that same thing as the weak operator topology?
No, it's almost the same, but not quite the same. The weak operator product, the weak topology, the one that you named, is the one where you put here finite rank operators. It turns out that an algebra, which is a subalgebra of B of H, is closed in the ultra-weak topology if and only if it's closed in the weak topology. But if I want to view it as a topological algebra, then the better topology to put on it is the ultra-weak one. Anyways, so a module for a von Neumann algebra is a choice of B of H and homomorphism from that algebra into B of H. Sorry, it's a choice of H and a homomorphism from that algebra into B of H.
Can you repeat that sentence? What was the first time?
A module over a von Neumann algebra is the choice of Hilbert space H and homomorphism from the algebra into the algebra B of H. And the homomorphism is supposed to be continuous with respect to that topology. A bimodule is whenever you have two module structures whose images commute. And so one should be from the left and one should be from the right. So it's an A-B bimodule. If A and B are von Neumann algebras, an A-B bimodule structure on a Hilbert space H is a homomorphism from A into B of H and from B up into B of H, such that the images commute. Yeah.
So when you have a bimodule, is there any compatibility between the pairing of the Hilbert space and the module structure?
Yes. The compatibility is that so A is my von Neumann algebra, and let's say that this is the homomorphism that exhibits H as a module over A. Then the compatibility is that if I call this alpha, then the compatibility says that alpha of A star should be equal to alpha of A star. So that's, the star here is defined using the inner product. So that's the compatibility. So it's a homomorphism of star algebras. So we know now what von Neumann algebras are and what bimodules are. You're probably familiar with the way in which, if I take the collection of all rings and all bimodules between arbitrary rings, that this forms a two category. Is that something that you guys have already seen? So if I have a bimodule M for some ring A and B, and another bimodule N between a ring B and a ring C, then I call this a one morphism from A to B, and I call that a one morphism from B to C, and the composite of those one morphisms is defined to be the tensor product over B. So you take the usual tensor product between M and N, but then you impose the extra relation that this be the case. So the quotient of the usual tensor product by this relation is the tensor product over B, and that is a way of composing these things and therefore viewing them as one morphisms in a category. Okay, so this is just the story in algebra. The story in von Neumann algebras is substantially more complicated.
Sorry, these were a priori different Hilbert spaces, right?
Sorry?
These are a priori different Hilbert spaces for two different bimodules.
Okay, so in algebra, A, B, C are rings, and M and N are abelian groups equipped with actions. And then this is the correct definition. In von Neumann algebras, then I would say that A, B, and C are von Neumann algebras, and M and N are Hilbert spaces equipped with actions in this sense. And then this is no longer what you should do. I'm just putting this on the board to tell you that this is not relevant. This is, sorry, I shouldn't do that. Anyways, I did it, so let me keep it on the board. There's another thing which, so maybe let's put a disclaimer. So this is in algebra, and by in algebra I mean not in this world. And the unit of the so A is an object, A is a ring, and the unit one morphism from A to itself is take A, view it as a bimodule over itself, and that is a thing that has a feature that if I tensor with it, I don't do anything. If I work with von Neumann algebras, so this is the place where you first see that things are going to be more complicated. Namely, it is not allowed to take the von Neumann algebra itself as a module over it. I mean, it is a module, but it's not one of those. It's not a Hilbert space. And we've decided that we're only acting on Hilbert spaces. So this is not something you can do, because A is a von Neumann algebra, and I'm only allowed to put a Hilbert space there. And it turns out that what one has to do is to feed this into some machinery that will produce a Hilbert space. So there's a canonical way of turning any von Neumann algebra into a Hilbert space. The resulting object has a name. It's called L2 of A. And this is a Hilbert space, and it's a Hilbert space equipped with two actions of the von Neumann algebra A. And I'm indicating that there's actions by putting little a's left and right. And that is going to be the unit in the two category of von Neumann algebras. So let's see. It probably doesn't make sense to me to tell you too much about that because of lack of time. So I'll just leave it like that to say there exists a construction that produces this thing. And I'm going to spend a couple more minutes to tell you. So, okay, so I told you about the fact that there exists something that replaces that. And now let me tell you a little bit about the construction that replaces this. And I'm going to sort of take this as granted. So the so-called fusion tensor product, also called a confusion of bimodules for von Neumann algebras, goes as follows. Well, so what you do, it's so let's put a different symbol just to emphasize the fact that it's not that. Here, the algebras A and C, they're not really important in the construction. They sort of come along for the ride. And the only thing that matters is what's here in between. And the same holds here. I mean, I just need to tell you what the confusion is of a right module with a left module. And if I have further actions on the two sides, then they just come along for the ride. And this is, so here's one way of saying what it is. It is the usual tensor product, the one that you know, between M and so let's see. N is a left A module. L2 of A is also a left A module, so it makes sense to look at A equivariant maps from this to there. A is also, L2 of A is also a right A module, and therefore this hom as whole has a left action, and then you take the usual tensor product over this. So, I mean, this still needs to be completed in some sense, this to make a Hilbert space. But this is the thing that you write down, and let me convince you that this is a sort of reasonable thing to do. So what you want is to have L2 of A be an identity for this operation. So let's take sort of that as an axiom and see that that given an element M in M and an element F in this hom, that it is natural to expect that M tensor F is an element in this thing here. So here's what you can do. Let's take M, and well, because we agreed that L2 of A should be a unit, that's the same thing as M fusion with L2 of A. And then you can do 1 on the first factor and F on the second factor. And if this is operation is a functor in some sense, then you expect this to land in M fuse N. Well, so now suppose I have an element in here, M. Then I can apply this map to that element. So in complete generality, whenever you have an element in M and a map from L2 of A to N, you expect to get an element here, namely the image of M under that. And this definition is a way of turning that around to say we define this to be the set of pairs MF in some sense. And you might complain that this looks horribly asymmetric, that M and N play very different roles. But it turns out that there's a way of rewriting it that's more symmetric but a bit more lengthy. So here is another way of writing it. I can write it as Hom L2A M tensor L2A tensor Hom L2A N, where all these Homs and all these tensor products are over A. And the way to go between this and that is, well, so what's the difference between these two things? Well, here I have M, and instead I have here this, Hom L2A M tensor L2A. And there's an obvious map from here to there. That is the evaluation. Plug this in there, and then you get M. And well, this evaluation map is maybe not quite an isomorphism, but after completion it becomes an isomorphism.
Does fusion product be characterized by some universal property?
Not that I know. Anyways, I think my time is up, so I should stop here.
Well, thanks very much. For the discussion part, it would be helpful for the videotaping if the speaker could attempt to repeat the questions. Any questions?
Yeah.
Just making sure I have the definitions. So that picture over there.
This one?
Yeah. Well, actually, well, the one above it.
This one.
Yes. So a closed. So closed one manifold is assigned. Actually, the one above. One more.
A closed two manifold. That's what this is. Yes.
So the empty one manifold is assigned complex numbers. Is this what's going on?
Everything that's empty gets assigned the complex numbers, except the empty zero manifold gets assigned the complex numbers viewed as an algebra, and the empty one manifold gets assigned the complex numbers viewed as a Hilbert space.
And over there, so in the picture, the rightmost picture on the top. So the left, so the left point and the right point constitute an object. Is that right?
That's right, but that's not the way I want to see it. So I want to see the union of those 2 points, the 2 blue points, as being an object, and those 2 points as being an object, and then the blue one manifolds. No, that's right, that's fine. The blue one manifolds form a cobordism between this zero manifold and that zero manifold. So maybe I can redraw it in the following way, and that would help you. So this is a two morphism in a two category. So that's the way people usually draw two morphisms. And so here. So this is a two morphism that has, at this point, this zero manifold. At that point, that zero manifold. Up here, I have this one manifold. Down there, I have that one manifold. And in the middle, we have the whole guy. Does that help a bit? And you need to put orientations on everything and check that the orientations are compatible. I hope they're compatible. I think they are. So, for example, this thing here in red is this thing that sort of looks a little bit like an identity. It's not quite an identity, but it sort of looks like a thickened identity. That thing here looks not at all like an identity. That looks like you first take these two things and then sort of kill them with each other and then create the two red guys independently using that bottom part. And then this is a two morphism between that thing that doesn't look like an identity and this thing that does look like an identity. Yeah, more questions? Yes.
Yeah. So as you said, like in your two-dimensional model, it was really important for you that you had all functions that the top and the bottom corresponded to C infinity functions on the interval. But how do I see that if I went one dimension lower? Like as you said, what did these really parameterize? I guess more precisely.
There's no parameterization there. There's no embedding anywhere. So up to isomorphism, there's only one way of interpreting that picture. I mean, what are we looking at? We're looking at a smooth one manifold that has one component, and I have a color here and a color there. So the local model is like everything is actually like a local model up to disjoint union. Everything is a disjoint union of copies of that. Here, it's very much not the case. Here you have many, many local models because
So I shouldn't be thinking about these as having like fuzzy neighborhoods the other way.
There is no fuzzy neighborhood. So the question of gluing things is a tricky one, and one way of solving it is to sort of have some as you say, some fuzzy neighborhoods that allow you to glue them nicely. And it's surprising that it is possible to define gluing without these, and that's called conformal welding.
So, in practice, meaning like in examples, how strongly do the bimodules depend on the parameterizations near the boundary as opposed to, say, a choice of tangent factor?
Okay, so yes. So Jacob asks, in practice, how strongly do the bimodules depend on the parameterization as opposed to just a choice of tangent vector at the endpoints? And the answer is they depend only on a choice of tangent vector at the endpoints. And it also turns out that in practice, C infinity is overkill. You don't need C infinity in order to make that work. I don't know what the sharp what the sharp bound is in sort of regularity class that allows you to make these things. But here's something that I do know works. If you take things that are piecewise C infinity and C1 at the finite number of points, then I know that the thing extends to that category. So for example, it is possible to glue two C infinity things by just identifying the tangent vectors and stay in that. But that's a sort of ugly category. You don't want that as your final answer. So, but well, you need to make a choice when you present a definition. And since I don't know what the best thing is, I'm just sticking to C infinity.
Yeah, which von Neumann algebra is assigned to the empty zero dimensional?
So that's something that you can answer by considering the fact that disjoint union goes to tensor product. So the disjoint union of anything with the empty manifold is the same thing itself. So I want something that doesn't do anything by tensoring with it. And the only answer is the complex numbers. So it's empty manifold goes to the complex numbers.
Is there any way to take the Hilbert space to be something very simple, like L2 functions on your manifold or something like that?
No. So conformal field theory isn't the sort of thing where you can just fool around and produce lots of examples. I mean, it's not like group theory where you can just like write down a presentation and hope you have a group. It is difficult to construct examples, and the sort of first examples that people know of and exist, they sort of they just belong to a given list that people sort of know. That's what you encounter first when you try to classify them. And then if you go a bit further, then people don't really know what you encounter, but there are things that are more complicated. So you certainly cannot say assign the L2 functions on that. The simplest thing that you can do is to assign the so-called Fuchs space, which is it's somewhat of a story, so maybe I won't say it right now.
Does the conformal welding works well in families? You're trying to define CFTs over some
Yes, does conformal welding work well in families? The answer is yes. That's exactly the thing that, let's see if these two authors are still on the board. So these two guys, Ratnell and Schippers, have a paper maybe 5 years ago, and that paper addresses exactly that question. So the answer is yes, and it has been done there, and it's quite some piece of work. So.
Right, there are no more questions. Let's thank the speaker again. Next up will be at 11:30. There is coffee upstairs in the lounge.